Welcome everyone to our webinar today. In the first part of this webinar, we'll see why there are grid code requirements and why is a simulation model, so a computer simulation model required by most of the grid codes. And first, a few words on the energy transition that we are all witnessing today. And with this, a figure to emphasize it. It is estimated that by 2050, 50% of our society's energy consumption will be through electricity, which is 20 times the electricity consumption from the year 2020. And this is a tremendous challenge then to accomplish. And most of countries around the world are experiencing an energy transition, which has the following three main drivers. First, as I said, the energy demand increase, fast growth in population increase the energy demand, of course, around the world. Secondly, the climate change here with the large-scale shifts in weather patterns and global warming that we all are aware of. And finally, then the energy interdependencies internationally due to the concentration of fossil fuels in unstable countries, as we saw during the last year. And all the three drivers then are pushing our government to take decisions and initiatives to reduce CO2 emissions, for example, and also improve our energy mix and energy supply. This in turn then results in new investments strategies for most companies, and the new investments then leads to big transformations of the electricity grid. For example, with the growth of the renewable power here, we put more stress on the power flows and more uncertainty on the productions. For example, with the photovoltaic power generation. Additionally, we discontinue the conventional power plant base and the polluting plants also, and providing then that we're providing before really the base loads and inertia to the grid. And finally, there are increase of the energy storage load due to then the switch to the e-mobility with electrical vehicles. And these transformations then are a very huge headache for grid operators, as we call them a TSO, which are then responsible to balance the electricity production and consumption at all time, all day and night. And to support all these variations in production and to improve also the quality of electricity delivered, these network operators needs the most accurate grid simulation model possible, and therefore requesting in return to the power producers to provide them the simulation model of their own power plant and going through a certification process to ensure its accuracy. This process is described in detail in most of grid codes that we see around the world. And the grid codes stipulate sometimes higher requirements than just a basic simulation model or a computer model to be provided. It's asking also for proofs gathered in a report, and power utilities owner are in need of different types of such report we call studies. The first one or first case would be a grid code compliance study to verify the compliance of their power plant via simulations on computer and on-site measurements. A second type of study would be a plant feasibility study during the design phase, for example, to verify the plant overall performances like equipment loading, harmonics content, to optimize the overall plant design. And finally, the grid impact study, sometimes required also by the TSOs to evaluate the impact of a newly installed plant or a new retrofit on the surrounding grid. All of these to optimize, of course, the overall plant operation and therefore the grid stability. And if we take a look to the examples of grid code requirements, there is a typical concern about the fault right-through requirements, for example, in European countries. We see here on the figure that the grid code requirements requires the power plant to stay connected, for example, in case to stay connected to the grid in case of a three-phase fault when the voltage of the point of connection is in the striped area that you can see here, for example. Only when the voltage leaves this profile, then it is allowed for the power plant to be disconnected from the grid. And to prove such compliance and compliance to these requirements, a simulation of the fault is performed to assess then the system reaction to such event. And this is also required in the grid code, as it is much easier than and less expensive than testing it in real life, or even sometimes not even possible. Some other examples of simulations validation requirements are, for example, the voltage step response analysis required in Australian grid code as example, where then an overlay of the no-load step response curve with the real measurement curve is required then before connecting the machine to the grid. Or we can also take examples in Mexico, where it is also required there to provide a simulation model before the equipment installation, which then will be validated later on during the validation process. What we saw also lately is sometimes also a frequency response analysis is required to validate the damping of a provided PSS function, power system stabilizer function, and provide then proof of its damping around a defined frequency range, which is required, for example, in Italy. Some things that we have nicely done here, as you can see on the right side with our CMT 1000 PSS tuning assistant that you can see here. So these were just examples of simulation model validation required by the authorities that cannot be achieved without an accurate model and proper testing. It is also examples that we have seen in ABB in the past. And to help here our customers, ABB provides also plant simulation solutions that may include a simple standard simulation model up to a complete grid code compliance study. From the model development here, which may be basic or a custom model, for example, for electrolyzer or wind turbine PV inverters, up to the model validation with final measurements overlap with the simulation, including then the different steady state simulation case study required, like load flows or short circuit studies, the evaluation of the FRT response, so inside the dynamic studies requirements, and also power system consulting are available to provide a tailored recommendation in electrical design. And to perform such a detailed study, there is a typical process is applied by us, where then first we gather the data availables and requirements from the grid code, for example. Secondly, the plant is modeled in the simulation tool on the computer, and all the systems are optimized after that. And the compliance simulations are performed when the systems are optimized. And this means here, compliance simulation, this means then performing and documenting all the tests and proofs required by the grid code in a report. And once the grid study is done, the grid code sometimes also requires the same test to be performed on site on real conditions. And that's where the compliance commissioning takes place. In this step, then it's very important to perform the correct test procedure as required by the grid code in order to be able at the end to overlay measurements over a simulation during the model validation. With all of this said, we will now talk about the typical project steps for an excitation system delivery for a power plant, for example. When taking a look to a typical project delivery scope of an excitation system, which can either be followed by ABB itself, but also our customers, such as our added value partners, system integrators, end users for many kind of applications like small, medium hydro, genset power plants, or even marine power applications. We can define in general these 7 major steps in the process. First, the analysis of the system specifications and requirements. Then secondly, sometimes a grid code compliance check is to confirm the designed performance of the system. Then comes the engineering, here including more detailed simulation and parameterization. And when engineering is complete, the manufacturing and testing here takes place, followed or finished by the factory acceptance tests. We follow then after that the erection and commissioning. During and after commissioning, we also have the grid code certification and performance tests performed. And finally, the units is handed over to the customer for commercial operations. And here we have highlighted the different steps where we think that our new CMT1000 feature will be very helpful for you, included, and this is included then in the UNITROL 1000 product for free, as you can see here. Let's dive in here to understand how we can use this better. For the system simulation, for example, there is often a simple fault right-through analysis check during the sales stage based on simulations to confirm that the basic dimensioning of the equipment fulfills the requirements. In the engineering phase, the grid code compliance study may be performed, and providing an entire plant model may be required depending on the grid codes, and therefore the AVR parameters are already needed at that stage. Secondly, during the commissioning phase, so this is here the fine-tuning of the project phase, and 2 possibilities here can be used in CMT1000. The PID calculations are based on machine parameters, so this is really improved PID tuning considering the measured excitation power supply voltage and excitonominal values. Or we can use then the new auto-tuning function where no machine data are needed at all. And thirdly, when we talk about the grid code certification process, here grid code typically requests plant model validations, as we said, so where we overlay the on-site measurement with the simulation results, and here then with the tuning report from the CMT1000, the main parameters are given directly to you to improve the model quality and speed up the model setup. For example, sometimes the end customer would say hires an external consultant to perform the plant simulation or validation of a project, and arriving the time of the model validation, there is a typical mistakes made and the simulation doesn't match the measurement for some reason. And that's where then the headache starts. The email ping pongs also starts between then the consultants and the end customer to the system integrator, and the system integrator to the OEM, meaning ABB, for example, which can easily cost weeks on the project in order to find out then the correct parameters at the end. And with the new feature implemented in the CMT1000, the simulation parameters are already available, reducing the human errors and risks to the certification and validation process overall. Having said that, I will now hand over to Rudolf, which then will present you how the AVR autotuning feature supports this smooth project execution I was presenting. Up to you, Rudolf.
Thanks a lot, Quentin, for this part. Very welcome to this webinar from my side. I'm Rudolf Möckli, the product manager of UNITROL 1000. So what we do now is we go a bit more in details. What are the benefits of this AVR autotuning features, and how is this linked to the IEEE model? As Quentin laid out, this, let's say, the accurate models in the world today is becoming more and more important, and especially how to set it up based on what you have on site. So on the real physics, let's say like that. So before we go into that, we need to dive a bit more in details of the AVR. And here is a, let's say, a simplified model or diagram of the AVR, where I show the principles how the AVR works. And the AVR works in such a way that it has an input voltage, can come from a shunt supply, PMG, a fixed supply, we call it auxiliary supply, and that input supply is then rectified over this rectifier bridge, and you have here DC voltage inside the capacitor in the AVR. And this voltage is actually the maximum output voltage which can be routed outside the AVR just by switching on this IGBT forever. This IGBT freewheeling diode is then actually controlling the output voltage of the AVR by the means of the PWM signal. So mainly, let's say this PWM signal is going from 0% to 100%. When the PWM signal is 0%, then output voltage is going to 0. If the PWM signal goes to 100%, then the output voltage is the maximum what you have here available in the capacitor. So principle, this is the way how we regulate. And then in the regulation modes, either you try to regulate here constant excitation current, or you regulate here on the output voltage of the generator. One point here which must be clear, the structure of the AVR would perform or would give out only positive excitation voltage. There's no way that you can bring out negative voltage. So now when we talk of an AVR system, then it's important to understand this factor K ceiling. Actually, this K ceiling comes from the IEEE norms or standards, and it defines the ratio between no load excitation voltage and the maximum excitation voltage which can be applied. In terms that your system is optimized, you have to have a certain ratio here. So in our manual, we state that this ratio should be between 5 and 15, and 10 is, let's say, the optimized way how to work that. And you can see like that, if the K ceiling factor is too low, then you do not have the dynamics of the system to react on faults in the network. If it's too high, then your system will be too nervous, because a very small difference in the input in the voltage here will react in a very nervous step at the outside, which goes then out to the system. So optimized way would be factor 10. However, many of our customers, they go it a bit in a different way. They check out what stands in the datasheet of the AVR, and there is the statement that you can apply 250 volt AC or 300 volt DC, and they just apply this voltage. But that is in principle a wrong approach. The right approach would be that you actually check out what is the excitation voltage of the what is the required excitation voltage for no load on the exciter machine, and based on that you can calculate back with this case healing factor what is the voltage which you have to have on this capacitor. So in that case it would be 10 times higher, so it's 164 volts. And then based on that, you calculate back with the rectification factor on the diodes bridge what would be for three-phase PMG the needed input voltage, and this is only 127 volt AC. For example, as I made before, when you apply 250 volts, then you would have a case healing factor of 20. And with that, you can create troubles and, let's say, unstable performance of the AVR. Now, next step is that we look a bit more what is the AVR model behind. And here we can distinguish between certain blocks. Let's say the basics is a typically PID regulator. That means a summing point with a set point and with a measurement. And the error signal goes to a PID block, and that creates an output signal. This output signals is in the AVR always divided by a factor case healing parameter. And this case healing parameter goes in line with the supply voltage here. And the supply voltage multiplication, what you have on the output on the power stage of the AVR and this case healing, these two things should match in a way that the output is then, let's say, this case healing parameter would compensate totally the supply voltage. There's also functions that when the supply voltage change, that you can adapt the case healing parameter inside, that the gain is then adjusted depending on different input supplies. So then you have a second factor in your system. We call it case healing 2. And this is considering the gain reduction due to the effect of the exciter machine. You have there certain parameters in the exciter machine. This will define a gain reduction. And you have a gain reduction due to the fact that the main machine has a saturation curve. And important is to understand why this case healing factor is so important. In IEEE models, you calculate everything based on a linear system, based on a so-called air gap line. And the air gap line would consider the saturation of the main machine plus this gain reduction on the exciter machine. In terms that you can set up an IEEE model, you have to know this factor and this factor. Going back, coming now to more details on the PID tuning tool and auto-tuning. The SIMD 1000 had already since few years this PID calculation tool inside or integrated in the CMT, and this was used to calculate PID settings in general. We actually updated this tool a bit more now. On one side that you can use it in offline, and also you can calculate then the case healing parameters, for example, the case healing 2. And here you have these new input fields for the power systems. What is the power supply, what you're using? What is the nominal voltage at the input in RMS values? And what is the no-load voltage on the exciter machine? With that inputs, you can calculate the full PID settings, and this is used in the pre-engineered phase or sales phase to set up a simplified model. When you have the whole equipment running with a machine, you can use the PID calculation connected with a generator and you calculate it directly on the generator. And in this case, you don't need to set up this power systems data because this is then already measured from the CMT and filled in directly inside the report. Now, when you go to the auto-tuning, then this is then a big step forward because here you don't need to fill in any machine data. And this is quite helpful, for example, for retrofit projects, for systems which you just arrive on site, you have no clue what is your machine data, then you can just start an auto-tuning. Auto-tuning will make some measurements on site, and based on the measurements, it will calculate then the PID settings. In principle, what you have to do, you have to follow these instructions here. We see that afterwards live, and then it gives you out the proposals for the new settings. So the case ceiling parameter is calculated, the whole PID for the voltage regulator, for the power factor regulator, and for the manual mode. Maybe one word to this power factor and manual mode PID settings. These settings are very important in terms that all the limiter, overexcitation and underexcitation limiter are working with a nice performance. If you don't tune actually this PF and VAR controller and the manual controller, then you cannot rely on the performance of the limiters. So that's why it's very important. But the tool itself will definitely calculate that and set that up correctly. When you have done all the calculation, you have here the measurements, what comes up. So we measure the TDO prime, we measure the TE, and we measure the so-called time constant of the generator in no-load condition. And this time constant we use to set up here in the integrator of the PID settings. So in the theory itself, let's say the integrator time constant actually compensates the time delay of the main machine, and the derivator would actually be compensating the time constant of the exciter machine. So that's why TA is typically equal to TG, and TB is smaller, a bit smaller than TE. When we now look a bit in the IEEE model, this might be now a bit complicated to understand, but when you look at the main parts here, then you will find it quite simple as I had drawn it before. Here at the output, there is a multiplication. Let's say this is the AVR part on the regulation part, and here you have this multiplication, what we have with the IGBT and the freewheeling diode, and the PWM signals comes from this side. In the IEEE model, this multiplication goes over that line here, typically to the terminal voltage of your generator. And everything is calculated in per unit. That means terminal voltage is 1, and the multiplication is typically here multiplied with 1. You can have also a fixed supply. Then you set up this KP as a fixed supply here, and it goes directly down here. And interestingly is in an IEEE model, you would never see, let's say, a supply voltage as such. You just see at the end of the day a VA max and a VR max. And with that, actually, you would define the maximum excitation voltage, what you can apply to the system. The gains as such is actually set up here in that PID block here with the KPA. And this gain must be then corrected with the exciter machine compensating factor and this saturation curve of the main machine. So you use this K ceiling too. But in the IEEE model, you will never see this K ceiling parameter as such, because since this multiplication at the output is just 1, you don't need to divide the whole stuff here with this 1 over K ceiling parameter. When we come now to the, let's say, link between real life and simulation models, then in the auto-tuning or PRD calculation, you can generate a report. In this report, you have certain information. For example, the AVR supply, maximum excitation voltage, is defined here in voltage, and you can see that. We calculate the case ceiling and the case ceiling 2 parameters, which you need then to calculate this VR max. And this VR max, for example, that is used in the IEEE model. Also the gains, these PRD settings as such. Of course, the report gives you the settings, what you have there. For the IEEE model, you have just to calculate the VP with the case ceiling 2, and then you get the gain of the IEEE model. The rest of it is the same. And then, of course, you can optimize, or let's say with the auto-tuning, by filling in also the exciter machine parameters. And with that, you have then a better match here with the case ceiling 2 vector, which gives then the influence at the end, the overall gains of the systems. All of that are in this report, and this is the base actually for setting up a simulation. The idea behind was we would like to base the model on physical facts, what you have inside, so that you can have, let's say, a fixed point where you say this is really correct. Because there comes always other concerns, what is correct, what is not correct. And this is a bit the part where we go in now. This is a sample what I did, a sample overlay, let's say, on measurement and simulation. I have here on my table a real-time simulator, which we see later on, where I did a simulation one side based on Power Factory, and where I did the real measurements with the real-time simulator and overlaid both of them and utilized actually what I've shown before. And the results are really nice. Typically, simulation match in the beginning is very simple. You can make that with the initialization of the model. But then, let's say, after the step response up here, that you still match it, that means your gains in the models must be correct to match that. So that is a very simple test where you can do with a step response when these parts are in the steady state the same values, then you know that the gains are matching quite nicely in your system. The overshooting part here at the beginning, and also when you shoot down, how that works, that is then mainly depending on the reactance, time constants of the main machine, excited time constant, and all these things. And there you might not have in the real life these nice overlays like I have here, because the tolerances of the parameters in the main machine and in the exciter machine are typically quite heavily. But here the match was nicely. There is one question maybe to the audience, why it's step up and step down is so different. And there's a very simple answer. In a UNITROL 6000 system where you would have positive, negative voltage, step up and step down would be equal. But in a UNITROL 1000 model, in the real life also, you have only positive excitation voltage. That means shooting up the voltage is dynamic and very fast. Lowering the voltage is then mainly related to the exciter time constant, because output of the AVR goes to 0 and hits here the 0 bottom line. So that's why, let's say, the step down is always slower than the step up. Okay, then let's go for a live demo. I have here set up with a real-time simulator based on the TEC 800 platform. Then I have a real unit 1000. The measurements are really analog signals to the AVR. I have an I/O box to control the whole stuff, and I have a real-time simulator to operate. I have an interface to operate a real-time simulator. This setup is used for the trainings, what we're doing here, and these trainings are offered here in Tori, but also more often as a remote training. That means people can access to our equipment over remote connections and can do then all the trainings by themselves, having more or less the same view what you see then in the future, what you see now. So let's do that now directly on the real-time simulator. This is my interface for the real-time simulator. I have here a standard machine from ABB Machines, a 10 megawatt machine, typically for unit 1000. This is the synchronous machine. I have a governor control, AC exciter machine, a generator breaker, and step-up transformer and infinitive bus. The system is now operating. You see that here that the field voltage and also the load angle is varying a bit. And I've connected here a CMT 1000 to the AVR. And important here when you work with Unit 1000, then the CMT 1000 is the commissioning tool to do, and a very nice troubleshooting tool as well. So this main window is always open and on the top, and you see that you are connected here to the AVR. And I'm here in the control mode. That means I can change parameter, I can change modes in the AVR, whatever I would like to do. For working with Unit 1000, I need this set point adjust window here, where I see the state of the generator, in which mode I operate, the limiters, set points, and I can apply steps here. A very nice feature is this oscilloscope part here. So I can start here triggering, and you see it also, it's now already working as it should. Important is these files here you can save to the PC, and I also recommend to do that save with parameters, because then it will save the waveform file. It includes about 120 signals there, and it would also save your parameters. And these two files are heavily required when you ask for support from our side, because with these two files, we find your problem in seconds. Then let's have a look on the tuning. In this tune menu here, you have now this AVR tuning assistance. And with the AVR tuning assistance, you can here, for example, go to this periodic calculation. We do first this periodic calculation very simply. I have pre-filled all the technical data already. The name of the machine is not 100% correct, but we can change that shortly. The rest is okay. Then you have to follow up here these instructions. So typically you bring up the machine to 100% speed, and typically for the first commissioning you would start anyway in the manual mode, because you're not 100% sure that the PT settings are correct, and typically you run the machine first at 50% voltage, and then you check all the measurements and that the machine is really running at 50%. So I switch on now to manual. Green light's coming up. So I am on 100% voltage. I have here the manual mode in, and step 5, it calculated the case heating factor. This is now 16.10. And now you have this checkbox here that you tell, let's say, the system, yes, we check that the voltage is at 100%. You can do that by use of maybe another protection relay which is already installed, or you have another equipment which you can check that the voltage is on the level what you like to have. After that, you press this calculation button, and it will calculate the PID settings. It will ask here for this U power at no load. This is this correction factor which would then correct case heating factor of the AVR depending on the input voltage. For the time being, I don't use that, so you can click no. and this is still switched off. Then what you see here on the left side, it calculated the PID for the voltage regulator, for PF, and for the manual mode, and it gives you also here a short simulation how that should look like. After that, you can either store the report or you just make the takeover. And then these two columns are, let's say, aligned, and the parameters get active. When I now switch back to the manual, to the auto mode, you see the top here, I switched it back. I can apply a step and check how the system is performing. What is of interest always in a no-load condition is what is the overshoot, and the target what we have set up is 15%. So I went from about 100% to 105.6. So that is between 10 and 15%. So quite nice overshoot, quite fast. So the PID settings was quite nicely done. And please notice that this PID calculation is quite heavily used, especially for the OEMs when they have typically calculated in the engineering phase and they do not change that any longer. And in the OEM, that's also business when you have repeating business with same machine, then typically you validate once setting and you reuse that settings for all the repeating orders. So that was actually working quite nicely. So let's see how auto-tuning is working. In the auto-tuning, I go back to the input here and click on auto-tuning. All the fields are disappearing because I said it before, auto-tuning is working based on measurements. I go back to manual mode, so same procedure as before. Okay, sealing factor is calculated. And then let's see, I click it on here. I would like to make it a bit long on the buffer side that you see what we will do. So what we do first step up, step down in open loop, that we need to measure actually the exciter time constant, and then in the second round we switch off excitation, and the fall down of the voltage is used to to measure the TDO prime. Both is measured with a data logger with 5 millisecond resolutions, and it will then calculate here back actually the correct values. And what you see here as a result, the TDO prime is measured, DG no load is measured with the 2.4 seconds. That is actually set here with the difference from the TA. TB was set lower to the TE, and we have here also the no load voltage measured. This is here with 1.4 volt very low due to the fact that I'm having here only 24 volts on my desk, and I'm running that on the real-time simulator. So I can take over the whole stuff. And then let's see how the stuff is now working. Just added the voltage back to 100%. Made the buffer length a bit shorter and apply step again. What you can do with the oscilloscope, or you have here the step response, what we applied, and of course you can overlay that just by drag and drop here also down, you see that it's nicely matching. The overshoot, what we have measured before, just to have that as a checker, is a bit higher, but going more than this 50% now, so it's a bit more accurate than before, and it improves compared to the PID setting the system a bit. but not dramatically. But in principle, this is the very fast way how to do that. In the report itself, what you can save, you have all the information with which tools you did it. For the input voltage of the input parameter of the machines, this is not applicable because it's measured. Then you have this measurement of the raw values. We actually normalize these values in terms to how to say to improve the measurements. And then you have this part of proposals, what should be set up and was the previous one. An important part is here below, giving all the information what you need actually for your system. That means your max actually was here defined, the AVR max was defined, case ceiling 2, and also the UA in how to say in per unit values. So with that actually you have really, let's say, a nice setup that you have a simple way how to set up a simulation model. Now coming to the end, let's say, what are the benefits, principle? So the tool, what is integrated in the CMT1000 provides you help during the engineering in terms to calculate PID settings, which you need in the sales phase even, and it would support you heavily during commissioning and improve also the parameters and performance of the AVR. The auto-tuning itself takes only a few seconds, as you have seen that in the live demo, and so it's very fast. And it identifies all the main parameters for the voltage regulator, power factor, VAR regulator, and for the manual mode. And this is important in terms that the limiters of the AVR works correctly. At the end, it also identifies the main parameters based on the physics of your systems. That means you have a really good starting point for setting up a simulation model, and that actually reduces the risk in the certification process heavily. And it might actually, let's say, reduce this ping-pong emailing between certification body, third party who builds up the model, the OEM who has to provide the final model to the TSO, and so on. So for that perspective, I think with this auto-tuning, we have hit a quite nice bridge between real life of your system towards the simulation model, and that means optimized solution to cover these needs in what we're seeing today, that you have to provide a simulation model for all the projects what you deliver. Now I summarized here all the new documents for the new releases. You can download all these documents from the ABB library. As a prerequisite, you have to be registered in the My Station widget. Then you get access directly to the ABB library. And this is actually, Barbara made a nice introduction and instruction how to register. And with this barcode, you can easily go to this site and register yourself. Now I hand over to Barbara for the final Q&A session. Let's see.
Thanks a lot.
What comes up now?
Thanks a lot to Rudolf and Quentin for this session. I see we have a couple of questions. There are still 7 minutes to go. So again, if you want to write more questions, feel free. Otherwise, you can share in the feedback form I've just shared in the chat. So 2 questions from Luca. For a brushless excitation system with an excitation voltage up to 50 VAC, is it possible to supply the UNITROL 1010 from DC battery at 110 VDC? In such case, we can guarantee the ceiling voltage required by grid call. What do you think?
Oh, that is a complicated one.
It's a complicated question.
What do you mean with excitation voltage up to 50 volt AC? That is the main question. I mean,
yeah, let me unmute Luca. if he's still with us. Just 1 second.
I mean, you have to consider the full tuning process is actually also the settings is going to no load excitation voltage. And you have to provide at least 10 times higher excitation voltage typically. If, of course, 50 volts is the no load, then we cannot do that. That's clear.
So nice to meet you, Luca speaking. I mean, for example, if we have a generator by a brushless excitation system, we have to supply the AC part of this brushless system. Supposing that the AC voltage of this brushless is more or less up to 50 volt AC, due to the fact that we have the DC battery inside the power plant of 110. In such a way, due to the fact 110 is more or less double than 50, we can reach the ceiling voltage required by our grid code requirements that may that sometimes is 160% or 200%. So in such a way, I can supply the UNITROL by a DC voltage directly instead of AC voltage.
Yeah, but what I do not understand here are two things. I mean, excitation voltage, what comes out of the AVR, is typically a DC voltage, it's not an AC. And you have to consider always, and that is, I think, the main key point, ceiling factors are defined in different ways. In 6000 systems or also in grid codes sometimes, they refer to the loaded point of the machine. Where in the presentation, what you have seen today, we refer to the no-load excitation voltage. And this has to be considered. And typically, the factor between loaded and no-load is 3 to 4, something like that. But this is actually very well described in this commissioning document, what we did. Also with the tuning instruction, especially how to calculate this ceiling. Then I think based on that, you can work out in more details what is really correct and what not. Principle to work directly from a 110 volt DC battery, I do not see any issue with the unit 1000 because you can apply DC or AC voltage. That doesn't matter.
Thank you.
Barbara, you're muted.
Sorry, apologies. I see that Luca has also a second question I don't think has been taken already with your answer. Maybe Luca wants to articulate that one as well.
Yes, I mean, in this way, you said before that the UNITROL 1000 is not able to provide a negative voltage. So in such way, maybe when we have to guarantee, for example, the load rejection, it means that the generator shall supply its own loads. Maybe this type of AVR cannot, let's say, help the negative voltage in order to keep the generator voltage within the limit. If we have a negative voltage in the excitation system, maybe the generator nominal voltage in the stator part, I mean, can be within the limit better than without this negative voltage. What do you think?
That is principally correct. I mean, load rejection is always a bit an issue. Typically, you would need to do a simulation, and it heavily depends actually on the main machine parameter, how good that can be done.
Sure. Okay. Thank you.
Thanks. Thanks a lot. We have 2 more questions. 1 minute to go. Does ABB have a similar tool for tuning process of UNITROL 6000 excitation system?
There will come up a so-called power flow tool, which will be the lot where also tuning on 6000 system will come up. But that is still, let's say, in the defining phase. And the tool will be based, let's say, on a web-based tool, which can be then accessed by everybody. But how that really looks like, that is still a bit open.
So stay tuned is the message. It
Yes.
will come.
It will come.
Thank you. And then very last question, this simulation tool works also for static excitation?
I mean, for static excitation systems, you would have different IEEE models, number one. In principle, you have also nice documentation how UNITROL 6000 system is represented in IEEE models. But the main difference is that the static excitation system has no exciter machine, and of course it has positive negative voltage as an output.
Perfect. Thanks a lot. I don't see any more questions coming, so we are perfectly in time. So let me thank again all our participants, our speakers, for joining us. So you have received already the feedback form request. If you have 1 minute to spare, let us know what you think of this session. And if you have questions, feel free to write it there and add your email address so we can come back to you. In a couple of days, latest beginning of next week, you will receive the presentation that has been used during this webinar and the recording. So thank you very much again. Wish everybody a good day. Thanks a lot.
Thanks a lot. All the best.
Thank you very much. Have a good day.